Today I'm going to be talking about Martian radial ejecta and kind of some interpretations I've been working on related to that. We have a broader project than this, and you can see my co-authors and co-workers on this project listed there. But for this particular talk, most of the new interpretations I'll be talking about are my own. So, just a brief review of terminology for those who may not know too much about ejecta. We've had a little bit of talk about it, but in general, there are two types of ejecta that we see currently in the solar system. And one is termed radial or ballistic ejecta, and this is the type of ejecta that forms as the material just comes out and ballistically lands back on the surface. And then the other type is layered ejecta, also known in the past as fluidized or rampart ejecta, because it does tend to have this flow-like appearance, like it was fluidized. So it included some kind of volatile as it was flowing across the surface. And the ramparts came from this idea that a lot of these, but not all, have thicker ends or ramparts. And these are just two examples, one from the moon and this other one is from Mars. And the important difference between the two of these for this talk and for my project is that radial ejecta is tend to form from in terrains that don't have a lot of volatiles in them. They're typically pretty dry, whereas layered ejecta are thought to form in terrains that have subsurface water or ice in their subsurface. There are other ideas out there, but that is the one we will be assuming for the purposes of this project. And then finally, you can have hybrid ejecta, which has both types of these ejectas together. And we'll see some examples of those in a little bit. And I just want to note that for these comparisons, I'll be comparing some original analyses and classifications done by Stuart Robbins from the Themis daytime infrared mosaic. And the newer work that I'm doing is using a CTX global mosaic, which is invisible. So I also wanted to provide a brief overview of the whole project and why looking at radial ejecta craters is of importance to us. So in a previous project published in Kirchoff and Grimm in 2018, we were trying to understand the age of layered ejecta craters and what that might mean for the evolution of subsurface ice, particularly at the equator where the ice is likely deep enough that the other kind of remote sensing techniques can't find it. And while we were doing this, we also found that when we plotted up the classifications from Stuart's database, that there was this intense mixing of layered and radial ejecta craters. So in this figure, you can see the red craters, locations of radial craters plotted in red, and the location of blue layered craters plotted in blue on a Themis mosaic. And so you can see, like, there are lots of radial craters forming right next to layered craters. And so and we weren't the first to see this, but we thought it needed more exploration at this point, because this could mean, assuming that layered ejecta craters formed by tapping subsurface volatiles, that there is either an intense mixing and or mobility of the subsurface ice and water. One way to particularly to determine what's going on here is to get the model crater retention ages of these larger craters, so counting small craters superposed either on the ejecta blankets or on the floors of these larger craters. To see if timing makes sense why you would find a radial next to a layered ejecta crater, like the ice has either disappeared over time or moved from another location to the current one. The problem came in, and I would note that while this is a problem, it's not a problem that prevents us from doing this project. It just changed the idea of what the spatial distribution might be, as I'll get to shortly, Um, when we used CTX to examine the classifications of Stewart's craters, we found that 26% of the craters in just this region that I pointed to here had a different type of ejecta or no ejecta. And most interesting was that the radial ejecta seemed to be more affected. So out of these 291 craters, 3/4 of them were initially classified as radial ejecta craters. 78% of these radial ejecta, well, actually 78% of all of the craters eventually were classified by me to possibly have no ejecta feature or nothing was there. So by non-ejecta feature, I mean it was possibly the topography of the surface around the crater rather than being an ejecta blanket. 14% were a different ejecta. So they went from radial to layered or layered to radial. And out of that 14%, 75% of them went from being radial to layered. So more craters went from being a radial to a layered ejecta. And often they were eroded a layered, which probably made them look more radial in the lower resolution. 9% went either to hybrid or went from hybrid to one type of the ejecta or the other. And finally, kind of most interesting too, was we went from a 60-40 split of radial to layered ejecta to more of a 50-50 split, indicating that could be more layered and less radial in a relative sense than we initially thought. And I just wanted to point to work that Leo Tornabed has been doing, looking at the ejecta of very fresh craters on Mars, and they're seeing that actually most of these, in some sense, are hybrid, where the radial component tends to be very thin, and so gets eroded quickly, and they look more like layered. So it's possible that more craters were initially a hybrid than originally thought, and what this might mean for subsurface volatiles is still unclear. So coming back to that earlier figure, this now plots the craters remaining that have ejecta. And again, we have the radials plotted with red dots, layered plotted with blue, and the hybrids are now in pink. And could this transition in classifications be one, possibly indicating mixing is not as intense as originally thought? We do see more regions where you just see radial or just see layered than we did in the previous figure. But there still, of course, is still quite a bit of mixing in most of the area. Another thing that we're wondering as well is, does this mean that radial ejecta is eroded faster than layered ejecta? And this is something that we're testing with this project as we get the ages. We'll use the ages of the radial ejected craters that we do have to see if we're not getting as many that are as old as layered ejecta craters. And I would note that our project is limited to about 3 billion years or so, because a lot of things on Mars are eroded that are older than that. So we don't see craters with ejecta that are much older than that. And then finally, I was just curious too, is my recognition of radial ejecta, particularly in CTX imaging, actually, valid? Am I interpreting things correctly, given that there's probably more expertise out there than my own on radial ejecta on Mars? So that was the point of the talk today, was to present some examples of some classifications I made related to these changes, and get expert input from people at this meeting. So I will be bringing up examples, and please feel free to put into the chat if you're like, oh no, she's crazy on that one, or yeah, I totally agree with that interpretation, as we're kind of going through the slides here. And I only have about 7-ish examples, so this hopefully shouldn't take too long. So first of all, we see an example here, and I will note on these slides, except for one, The figure on the left is always Themis and has the original classification from Stewart, and the figure on the right is then the CTX image of that same crater, and it would be how I did my interpretation. So this one went being interpreted as a radial ejecta crater, which you can kind of get from some of the feathering that occurs around and hummockyness that occurs around this crater, to no ejecta, because I thought as you zoomed in and looked at it, this crater at higher resolution, these all mainly looked, this hummockyness all mainly looked like underlying terrain and not actually ejecta from this crater. Just another example of that radial ejecta to having no ejecta. And again, it seemed to me like the underlying terrain was the hummockyness that looked like ejecta in the lower resolution Themis imaging. And this is one where I'm comparing two CTX images. And so this is the same crater from the previous slide, that was potentially a radial ejecta crater. And I would say and this is on the left side, is a layered ejecta crater. So you can kind of see that sinuosity of the edge of the ejecta and that it flowed. And now this isn't a fresh radial ejecta layered ejecta crater, but it seems to be about the same age, maybe even a little older than the radial ejecta crater on the right. So I was just noting that maybe this is one of those hints that if this was initially a radial ejecta crater, which we don't know because we don't have any more clues to tell us, but if it was, it lost its ejecta faster than this layered ejecta crater. If it was layered, then there might be something going on in one area of the planet versus another, such that the ejecta got erased faster there. So moving on, we have one that went from radial to layered. And I think part of what was going on is the ejecta from this crater was potentially getting confused with the ejecta from this crater in the lower resolution. And it might not have been clear that this flow feature was associated with this crater, whereas in higher resolution, I think you can see that much more clear connection between this crater and that crater, that part of the ejecta. And here's one of those examples where it went from radial ejecta to eroded layered ejecta. And the reason why I thought this was a layered is, again, you're seeing kind of the pancake sinuosity at the end of the layered ejecta that is typical for that type of ejecta, plus this kind of pitted erosion that happens to many layered ejecta craters as well. So, and then this one went from radial to hybrid. And again, I think, you know, you can pretty clearly see some of the radial aspects in the Themis imaging. But actually, when you get that higher resolution of the CTX, you see that some of these features farther away from the crater are actually have that little bit more layered morphology, with a little bit being more sinuous and flow looking. So that was kind of why that one went in that direction. And just another example of radial to hybrid, where again, you can kind of see a bit more clearly in the Themis image the radial aspects of this ejecta, but when you get the higher resolution CTX, you start to see some of those flow features that are associated with the layered. I think particularly like this lobe here looks very flowish to me, very layered morphology. And then finally, I had some that I just didn't know quite what to do with. Now, a crater like this would not be included in the work studying the ages of these craters. One, because if there is ejecta left, there's not enough to try to perform a crater, get superposed craters and get a reliable age for this crater. So, but it's still an interesting case of something that looked like it had a bit more of that radial feathering in Themis is now seems to have almost none of that in CTX, except for this still small aspect in the northern part. So I don't know if you guys can see my pointer. Hopefully you can.
Yes.
But so is this a remnant of radial, or is this still just the topography tricking us into thinking there's something there? And just another example of that. Again, some feathering, some hummociness that looks like radial ejecta in Themis. You look at it more closely at CTX, and it almost seems like this is instead some kind of underlying topography surface that even continues beyond where you expect ejecta for the crater, but it does seem very circular and associated with the crater as well, so not fully sure. And just one more example of that, again, where you're seeing the feathering in Themis and maybe still seeing it in CTX, especially here in the south of the crater, but didn't know quite what to do with that crater either. As one example of hybrid, so this crater was originally listed as hybrid with both layered, which you can see the layered aspects here on the lobes, to radial with what looks like maybe some feathering radial extending out beyond that. And when you look more closely in CTX, or when you look at with better resolution in CTX, you see that although these are kind of definitely somewhat radial features, they're actually very sinuous, and they have a very ridged kind of linearness that is not quite as common in true radial ejecta. So this was actually one I talked to Nadine a bit about, and she was like, no, that looks all layered to me. You're just getting kind of these thin layered rays. We also see craters on Mars that people call splash craters that have this similar kind of very thin lobes rather than thick lobes. And this was just one example where showing that this can also happen with a layered morphology, where this kind of extended terrain here, particularly to the west, looks like a layered morphology with a rampart, but at CTX resolution, that rampart doesn't quite look as strong, and it's not clear if that's some kind of part of underlying topography or part of ejecta for this crater, which of course is heavily filled in, so you would have to wonder if ejecta would remain. So just back to the kind of the question slide, you know, I haven't really answered any questions yet. As I said, is radial ejecta eroded faster is being tested, which I'll talk about next. But I just want to know, what are your thoughts? And if of some of these interpretations I've showed today, and if you don't want to talk about it here, you can email me. And I look forward to hearing comments about that. And finally, just kind of what to look for in the future. So we hope to be presenting at LPSC kind of initial results from the first 5 groupings of our work. So we don't have the time to get the ages of all the craters in this region. So we've split them into groups across the region to try and to then do some interpolation, which Jamie will lead to help us understand possibly the evolution, spatial and temporal evolution of subsurface volatiles in this area, which is near the equator, and this preliminary analysis of the radial ejecta erosion question. So with that, I'll put it back to the slide and see if there's any comments or questions.
Thank you, Michelle. Fascinating. Starting to sound like a Vulcan, I guess. Stuart, would you like to
Sure.
lead us through this?
So there was several back and forths in the chat about specific things. Of course, without timestamps and slide numbers, it's hard to say whether people were specifically agreeing or disagreeing with you. But I think something that this emphasizes and something that I mentioned in the chat is that some of this is certainly subjective, and you're going to get this natural variation in how people classify things. But I think that it's not just subjective based on how you or I would classify things. It's also certainly subjective based on the data that we have, as the majority of your talk pointed out. And I think that that leads to something that a couple people were mentioning in the chat is the sun angle. So, for example, pick out Jen Piatak. Sorry for pronunciation again. She wrote, many of the CTX images look to me like the sun angle is high and we're missing shadows and contrast to see the textures of radial ejecta. So I guess I'll broaden that. How much of this do you think is an illumination effect from the CTX time of day versus Themis time of day?
I think that's definitely a probability, or I would say plausible, I would say, because I just, as I think you would notice from looking at the CTX imaging, a lot of it is taking at higher sun in general, and isn't the best for identifying very fine topography. So I think that can certainly be a problem in this case. And then I don't know if going back to Themis helps, because, you know, with the lower resolution, it also makes it a little harder to see those finer features. And I would note that some things tend to get hidden by using the IR rather than the visual. So we're kind of stuck. And I haven't looked in detail like high rise if this would help this problem. Of course, high rise coverage isn't global. So I'm not 100% sure what to do. I can only work with the data I have, which I never thought I would say for Mars, but because I worked with much more limited data elsewhere. But of course, I'm trying to answer a much more detailed question here. So so if anybody has any thoughts on that as well, please let me know. But
yeah, so it looks like Jim had wanted to contribute to that. I will say real quick that another issue, of course, is wavelength. As you said, the Themis, things do look different. You are dealing with a different wavelength of light, a very different wavelength of light. And Jen, I think it was Jen, mentioned that you also have issues with Themis is not just a reflection of albedo and shadow. You have temperature effects. I mean, Themis is a thermal instrument. And so you have that confounding things a little bit. And I will, looks like Jim is unmuted, so he can contribute.
Yeah, I just wanted to say a couple of things. One, I agree with the idea about the illumination geometry. I think it's really critical that, it's kind of clear that there's some variation there, just like in this slide alone. I'd also encourage you to stretch the hell out of the CTX images because, you have to be careful about what you see, but generally it helps the contrast. And I think you might start to see a lot of the things that appear to be missing, just as a general thing. And while I have the floor, one other thing I'd like to add here is that in the overall context of these hybrid types of craters and variations in general, once you establish the really great criteria to distinguish among them, remember that because of the spin axis orbital parameters, particularly obliquity on Mars, that snow and ice is being deposited at different latitudes throughout the Amazonian. So we've documented, mid-latitude glaciation, high-latitude glaciation, tropical mountain glaciers. And so ice is literally moving back and forth. It's being deposited tens of meters thick and then going back to the poles depending on the obliquity. And what that does is it can have a huge effect, not only on maybe the way the ejecta is in place in lobate craters, but also preservation of secondaries. So if you have a crater forming in a glacier, regional glaciation ice sheet, which is like 10, 20 meters thick, you're not going to preserve the secondaries, et cetera. So just keep those things in mind because there is a lot of geological options to why you would expect this a lot of this diversity. Thanks.
yeah, no, those are all great thoughts. And I certainly have been playing with the stretch with the CTX as I've been working with these as well. And I think that it does help show very some features you miss. So, but yeah, it's a good thing to remember to do that. And I know the distribution of the ice and its movement and all that is super complicated on Mars. And of course, a lot of that is Bob Grimm's problem. But him trying to understand the obliquity effects and like when things would have been placed and where things would have been available. And I'm just hoping with these ages too, we can provide more constraints on some of those observations of how and when the ice might be available or not available.
Yeah, absolutely. So, that's a really good point. And I think, we surely have documented the presence of these things, and there are a significant number of ages. And, it's a great situation to try to compare these data and really build up the stratigraphy for sure.
Mm-hmm.